Hello everyone, welcome back to another session of an online class. In last video, I explained about coupled circuits. In this video, you're going to learn about the resonance and the series resonance as well as the parallel resonance. So first, let us see what is this resonance called. So the resonance describes the phenomenon of increased amplitude that occurs when frequency of a periodically applied force is equal or close to the natural frequency of the system on which it acts. Okay, in this we have a series resonance and a parallel resonance. Before going into the series and parallel resonance, first let us see the Q factor first. So the Q factor or the quantity factor is a demonstrate dimensionless parameter that describes how underdamped an oscillator or a resonator is and characterizes the bandwidth of a resonator relatively to its center frequency. So a high value of a Q indicates a lower rate of an energy loss relatively to the stored energy. That is, the system is lightly damped. The parameter is defined by the equation, which is Q is equal to 2 pi into maximum energy stored by the total energy lost per cycle at the resonance. So here the higher the Q factor, the greater the amplitude at the resonant frequency, and the smaller the bandwidth or the range of frequencies around the resonance occur. So now let us see the series resonance. So here I mentioned a circuit which is in series of RLC, resistance, inductance and capacitance are in series. So here resonance occur in series circuit when the supply frequency causes the voltage across L and C, that is an inductor and capacitor, to be equal and opposite in phase. Since the current flowing through the series resonance circuit is a product of voltage divided by the impedance at the resonance, that the impedance Z is at the maximum value, that is equal to R. So therefore the circuit current at this frequency will be at a maximum value of V by R. So the frequency response of a curve which I mentioned here is a series resonance circuit shows that the magnitude of the circuit is a function of a frequency, and the plotting on into the graph shows that the response starts at near to zero, reaches the maximum value at the resonance frequency. So when Imax is equal to IR and then drops again to the nearly zero as F becomes infinite. So the result of this is that the magnitude of the voltage across the inductor L and the capacitor C can become many times larger than the supply voltage even at the resonance, but they are equal and at opposite, they can cancel each other out. So as a series resonance, the circuit only functions on the resonant frequency. So this type of circuit is also known as an acceptor circuit, because at the resonance the impedance of the circuit is at the maximum, so it's easily accept the current whose frequency is equal to its resonant frequency. Okay, so now let us see the bandwidth of this series resonance. So the frequency response of the circuit current magnitude relative to the sharpness of the series resonance circuit. So the sharpness of the peak is measured quantitatively and it is called the quality factor Q of the circuit. So here the quality factor relates the maximum or a peak energy stored in the circuit to the energy during each cycle of the oscillation, meaning that it is a ratio of a resonant frequency to the bandwidth, and the higher the circuit Q, the smaller the bandwidth, which is Q is equal to FR by BW. Okay, BW means the bandwidth. So as the bandwidth is taken between the 2 minus 3 dB points, the selectivity of the circuit is a measure of its ability to reject any frequencies either side of these points. So a more selective circuit will have a narrow bandwidth, whereas a less selective circuit will have a wider bandwidth. So the selectivity of a series resonance circuit can be controlled by adjusting the value of the resistance only. So keeping all other components the same, since Q is equal to XL or XC by R. Okay. So here I mentioned the series resonance as well as an resonance with RLC circuit. Okay, first one is the bandwidth of just a series resonance, and the next is the bandwidth of a series resonance, which is about RLC, series RLC resonance. So here the relationship between the resonance bandwidth, selectivity, and the quality factor for a series resonance circuit being defined as a resonant frequency. There are some points which are you going to learn about the resonant frequency, current, lower cutoff frequency, upper cutoff frequency, bandwidth, and the quality factor, which we are seen in which we are going to seen in this bandwidth of RLC series resonance. Okay, so first let us see this resonance frequency FR. By seeing this resonance bandwidth which of RLC, that is the second diagram. So here the resonant frequency FR will be XL is equal to XC, and that is equal to omega r L minus 1 by omega r is equal to C, where omega r square is equal to 1 by LC. Therefore, omega r is equal to 1 by root over LC. This is the resonant frequency of FR. Next, coming to the current I, based on this graph, current I at omega r is equal to Zt is equal to minimum and Is is the maximum. So coming to the I max, we have V max by Z is equal to V max by root over R square plus XL minus XC whole square, that is equal to V max by root over R square plus L omega r L minus 1 by omega r into whole square. Okay. So next, coming to the low power cutoff frequency at half power Pm by 2 is equal to I Pm by 2 at half power Pm by 2 I is equal to Im by root over 2, that is equal to 0.707 Im. So Z is equal to root over 2R and X is the minus R, that is in a capacitive value. So omega L is equal to minus R by 2L plus root over R by 2L whole square plus 1 by LC. This is about the low cutoff frequency. And coming to the high cutoff frequency, which is also known as an upper cutoff frequency, at the half power Pm by 2, current will be I is equal to Im by root over 2, that is equal to 0.707 Im. So Z is equal to root over 2R, where X is equal to plus R, that is an inductive. So here omega H is equal to plus R by 2L plus R by 2L plus root over R by 2L whole square plus 1 by LC. This is about the upper cutoff frequency. Now let us see the bandwidth. Here bandwidth is equal to FR by Q, bandwidth FR by Q, FH minus FL, and RL in radius or RL by 2 pi L in hertz. Okay, coming to the quality factor, Q is equal to omega R by L, omega R L in by R is equal to XL by R, that is equal to 1 by omega R CR is equal to XC by R, that is equal to 1 by R root over LC. This is about the quality factor. So this is the complete concept of a series resonance. Now let us see the parallel resonance. So here the parallel resonance occurs when the supply frequency creates a zero phase difference between the supply voltage and current producing the resistive current. So here I mentioned a parallel RLC circuit. So here the admittance will be Y is equal to 1 by Z, that is equal to root over Z square plus B square, and the conductance will be Z is equal to 1 by R, and inductive suspectance will be BL by 1 by 2 pi FL, and capacitive suspectance will be BC is equal to 2 pi FC. So in this parallel circuit containing a resistance R and an inductance L and the capacitance C will produce a parallel resonance, also called as an anti-resonance circuit. Remember again, parallel resonance is also called as an anti-resonance circuit. Okay, so when the resultant circuit through the parallel combinations is in phase with the supply voltage. At the resonance, there will be a large circulating current between the inductor and the capacitor due to the energy of the oscillations. Then the parallel circuit produces the current resonance. Okay, so coming to the condition for the maximum impedance. Uh, Here, note that if the parallel circuit impedance is at the maximum at the resonance, then consequently the circuit admittance must be at its maximum. And one of its characteristics of the parallel resonance circuit is that admittance is very low, limiting the circuit currents. So unlike the series resonance circuit, as a damping effect on the circuit bandwidth, making the circuit less selectivity. So also, since the current is a constant for any value of an impedance Z, the voltage across the parallel resonance circuit will have a same shape as the total impedance, and for parallel circuit, the voltage waveform is generally taken from across the capacitor. Okay, so this is about the condition of a maximum impedance. Now, for the current in an anti-resonance, that means a parallel resonance circuit, current in a parallel resonance circuit, as for the total suspectance is zero at the resultant frequency, the admittance is at its maximum and is equal to the conductance G. So therefore, the current flowing through the circuit must also be at its minimum, as the inductive and the capacitive branches currents are equal to IL is equal to IC. Also, current is equal when the current inductor is equal to the current passing through the capacitor, and are 180 degrees out of the phase. Okay, so the total current flowing in the parallel RLC is equal to the individual branch currents, and for a given frequency is calculated as IR is equal to V by R, where IL is equal to V by XL, that is equal to V by 2 pi FL, and IC is equal to V by XC, that is equal to V.2 pi FC. Okay, so therefore IT is equal to vector sum of IR plus IL plus IC. Uh, then we get IT is equal to root over I square R plus IL plus IC whole square. So at resonance current, IL and IC are equal and cancelling, giving a net reactive current equal to 0. Then at resonance, So here the this equation, that is I of t is equal to root over I square r plus IL plus IC whole square will becomes IT is equal to root over IR square plus 0 square is equal 0 square, that is equal to IR. Okay, so since the current flowing through the parallel resonance circuit is a product of voltage divided by the impedance at the resonance, the impedance that is at the maximum value, that is equal to R. So therefore the circuit current at its frequency will be at the maximum value of V by R, and the graph of the current against frequency is a parallel for a parallel resonance circuit will be given as here. Okay, so this is the graph of a current against the frequency of a parallel resonance circuit. Okay, now let us see the bandwidth of this parallel resonance. So the bandwidth of the parallel resonance circuit is defined in exactly the same way as for the series resonance circuit. So here the upper and lower cutoff frequencies are given as F upper and F lower respectively. So donate the half lower frequencies, whereas the power is dissipated in the circuit is half of the full power at the resonant frequency, that is 0.5 into I square R, which gives us the same minus 3B points at the current value, that is equal to the 70.7% of its maximum resonant value, which is 0.707 into I square, 0.07 into I whole square is equal whole square into R. Okay, as with the series circuit, if the resonant frequency remains constant, an increase in the quality factor Q will causes a decrease in the bandwidth, and likewise a decrease in the quality factor will cause an increase in the bandwidth, as defined by the bandwidth is equal to FR by Q, or bandwidth is equal to F upper minus F lower. So also changing the ratio between the inductor L and the capacitance C, or the value of the resistance R, the bandwidth and therefore the frequency response of the circuit will be changed for a fixed resonant frequency. So this technique is used extensively in turning circuits for a radio and the television transmitters and the receivers. So the selectivity or a Q factor for a parallel resonance circuit is generally defined as the ratio of circulating branch currents to the supply current, and it is given by the Q factor is equal to R by 2 pi FL, that is equal to 2 pi FCR, and that is equal to R into root over C by L. So note that the Q factor is a parallel resonance circuit is the inverse of the expression of the Q factor of the series circuit. Okay. So also in series resonance circuits, the Q factor gives the voltage magnification of the circuit, whereas in the parallel circuit it gives the current magnification. So this is the diagram of the bandwidth of a parallel resonance, as you can see here. So this is about this resonance class. I hope you understand this class. I will see you in my next class. Thank you.